Hello everyone, welcome back to the course Information Theory and Coding. In the last class, we discussed about the extension of the zero memory source. So in a brief, what do you mean by extension of zero memory source is that if a source emits certain number of symbols means, and if the source wants to extend the number of symbols which has been emitted, or if we want to increase the number of symbols of the source alphabet means, then we go for the extension of zero memory source. So here is one examples. In the last class we discussed about, so we have a source which emits the two symbols S1 and S2 with a probability P1 and P2. And if we want to go for the second extension means, then in the second extension the number of source symbols will be given by this formula, that is the number of basic source symbols to the power of extension. So basically how many symbols we have considered is, we have considered two symbols S1 and S2, therefore 2 to the power of second extension we are going, so 2 to the power of 2 is 4 symbols you'll be getting. See, what are those symbols? It is nothing but S1 S1 with a probability P1 P1, S1 S2 with a probability P1 P2, S2 S1 with a probability P2 P1, and S2 S2 with a probability P2 P2. And we all know that the sum of probability of all the source symbols which has been emitted by the source, it has to be equal to 1. So that is why we have tried it over here. So this will leads to a equal to 1. So we can come to a conclusion that even if we extend the source symbols, the probability holds good for all the probable values of the source symbols. And the next thing is, we need to find out the relationship between the zeroth memory source, that is the extension of S of S, and the second extension H of S square. So for that, so let us try to find out the entropy of the basic binary source, so which is having two symbols S1 and S2 with a probability P1 and P2. And we know that H of S is nothing but summation I is equal to 1 to 2 Pi log 1 by Pi. If I substitute that, we'll be getting P1 log 1 by P1 plus P2 log 1 by P2. Similarly, we studied about, so what is the entropy of the second extension of the source? So that is nothing but S square is equal to summation I is equal to 1 to 4 Pi log 1 by Pi. So now the source symbols we need to consider these, and with the probabilities P1 square, P1 P2, P2 P1, and P2 square. So we have arrived at an expression that is finally we will be getting the extension of the second source entropy, which is nothing but 2 into P1 log 1 by P1 plus P2 log 1 by P2. So it is nothing but entropy of the second extension is nothing but 2 into H of S. So H of S is the entropy of the original source. Similarly, we can come to a conclusion that the third extension can be given as H of S cube is equal to 3 into H of S. So in general, we can draw a conclusion that for the nth extension of the source, H of S to the power of n is nothing but n into H of S. So this is what we have studied in the earlier classes. So now let us try to solve one problem which is associated with this extension of the memory source. So now we have a discrete memory source which is emitting three alphabets S1, S2, S3 with a probability P1, P2, P3. Those probable values are given over here. So the probable values of emitting S1 is 1 by 2. The probability value of emitting S2 is 1 by 4, and for the S3 it is 1 by 4. So now what they are asked is, find the entropy of this source and also determine the entropy of the second extension and verify that H of S square is nothing but 2 into H of S. So you need to find out individually H of S and you need to find out individually H of S square, and then you should make sure that whether the extension is holds good for this equation or not, we need to find it out. So let us try to find out the first one, the basic source entropy with three symbols. So we know that summation I is equal to 1 to q Pi log 1 by Pi. Since the number of source symbols we have a 3, so therefore H of S is nothing but I is equal to 1 to 3 Pi log 1 by Pi. So if I substitute the probability values, you'll be getting the source entropy H of S is equal to 1.5 bits per symbol. Now go for the second extension. So as I said, the second extension will be the original source symbols. So how many original source symbols? 3 to the power of the what we going to second extension we are going. So therefore 3 power 2 is nothing but 9 symbols you'll be getting. So what are those 9 symbols? It is nothing but S1 S1, S1 S2, S1 S3, S2 S1, S2 S2, S2 S3, S3 S1, S3 S2, S3 S3 with the probabilities values are given it out over here. So now if I find the entropy of this, so since there are 9 symbols are there, so therefore the j term will takes the value 0 to 9 Pi log 1 by Pi. If I substitute all these probability values over in this expression, so you'll be getting H of S square is nothing but 3 bits per symbol you'll be getting. And they have said verify that h of s square is equal to 2 into h of s in the given problem. So therefore, h of s square is nothing but 2 into h of s. So what is h of s square? We have a 3-bit per symbol which is equal to 2 into the original source symbols. What we have? It is 1.5 bit per symbol. So if I substitute that, LHS is equal to RHS. Okay. So therefore, we can say that even the second extension will holds good for this property. And we can note over here is the sum of all the probabilities of the second extension source must be equal to 0. So means what? When you add the probability values of the second extension also should be equal to 1. Why? Because we know that the sum of probability of all the symbols should be equal to 1. So let us go for the next one more problem. That is, you have an analog signal. It is a band limited signal of up to 500 kilohertz and is sampled at a Nyquist rate. So we have analog signal. It has been sampled at a Nyquist rate. The samples are quantized into 4 levels. Means we have 4 levels, and the quantization levels are assumed to be independent, and they occur with a probability P1, P4 with a probability 1 by 8, and P2 and P3 with the probability 3 by 4. Find the information rate of the source. So they are asked you to find the information rate of the source. So if you remember, what is the information rate of the source? It is nothing but capital RS is equal to small rs into h of s. You need to find out. So first, let us try to find out what is the entropy of the source. So since the source it is emitting 4 levels quantization level, so the 4 symbols it is emitting with a probability 1 by 8, 1 by 8, 3 by 8, and 3 by 8. So if I substitute in this formula, so you'll be getting h of s is equal to 1.8113. So the next one is we need to find out the average information rate. So if you want to find out the average information rate, first we need to find out the information rate at which the symbols are emitting. That is a small rs. We need to find it out. So in order to find the small rs, they have given the analog signal is band limited to 500 hertz, and they also said that, and this analog signal it is sampled at a rate of Nyquist rate, means it is twice the maximum highest frequency component. So if I substitute 2 into 500, so you'll be getting 1000 symbols per second the source will be emitting. So therefore, the information rate small rs, capital RS will be given as small rs into h of s. So you'll be getting 1000 into 1.8113. If you do that, then you'll be getting the average rate of information will be 1811.2 bits per seconds. Okay. So this is all about the extension of the zero memory source. So we studied about, yes, this property holds good, and we have solved 2 problems. And for more problems, you can go through the assignments which has been given. Okay. So now let us go for one more important concepts what we are going to study. So still now, whatever we have studied the entropy of the given source, it was a memoryless source. So means what? If a source emits any symbol, means then it does not depend upon the previous symbol what it has been emitted. But practically, this is not possible. All the symbols which has been emitted from the source, they are dependent on somewhat others. For example, if in a WhatsApp, if you type some 2 key alphabet, then the third alphabet will be predicted based upon the previous 2 alphabet what you have typed. So like that, we have a source symbols which emits depending upon the symbols which has been emitted in the earlier cases. So such a sources or such a model or such a transmitter, we call it as a Markov source, or we call it as a Markov source model. So what do you mean by Markov source model is, so if a source is emitting a particular symbol x in the 0th position of the message, and it depends upon the previous q number of symbols, means the emission of this occurrence of the symbol x1, if it depends upon the previous q number of symbols, means then we say that the source is known as the qth order Markov source or a Markov model. And we need to specify these dependency of the emission of the symbols. It is not only the independent probability values we need to consider, it is also possible for us to consider the joint probability of the values. Why? Because the emission of the particular symbol, it depends upon the previous symbols. So therefore, we need to consider the conditional probabilities of emission of the particular symbol over the q number of interval. So therefore, you can see here, since pi depends upon the earlier q symbols, so therefore, we have taken the conditional probability over here. So now let us try to find out how we can find out the entropy of the average dependent source, and also the information rate also we need to find it out. So the first thing is what we are going to do is, so the average information content of the symbol which will be emitted by each state. So the Markov source model will be done in the form of state transition diagrams. So each source will be having some states, and in each state a source will be emitting certain number of symbols with a probability. So let us try to find out what is the entropy of the each state, and then it is possible for us to find out the entropy of the entire source. So therefore the entropy of the each state will be represented in terms of Hi. So this entropy of the each state is nothing but at that state, so what are the symbols with the probabilities are emitted, that we are going to calculate in the entropy. So that is nothing but Hi is equal to summation j is equal to n Pij log 1 by Pij. Since why we have taken the two terms is, so since we have a several number of entropies and each entropy will be emitting certain number of symbols, so therefore we will be considering this Ij, and also this I indexing will be considering. So similarly, we will be calculating the entropy of all the states, and finally the entropy of the entire source will be given as h of s is equal to pi into hi, where capital Pi is the probability of being in that state multiplied by the entropy of the source. So we will be getting the entropy of the entire source. Similarly, the average rate of information of the dependent symbol will be calculated as capital Rs is equal to small rs into h bits per second. Next, when you do this Markov source, that is a long independent sequence, it is necessary for us to find out with what probability the source is emitting and what is the condition. If I increase the number of source symbols, whether the entropy will increase or decrease, it has to be calculated. In order to calculate that, we are going to use one of the important theorem that we call it as a entropy of the adjoint source, we are going to call it as. Now you can see here, if P of mi is the probability of the source symbol of mi of n symbols, then it has to holds good this property. It has to holds good this property. So how you are going to find out this, all this thing is, let us try to look it in the problem in the next class. Thank you everyone.